Charles Steinmetz. Elementary lectures on electric discharges, waves and impulses, and other transients. All books on my channel are in public domain. Subsequent sections of the books are organized in playlists. Links provided in the last minute of the recording. Please, subscribe, like and comment. Please be mindful that this book was printed in 1915. Some conceptions and units might be different from what is considered a standard today. Lecture 2. The electric field. 7. Let, in Figure 7, a generator G transmit electric power over line A into a receiving circuit L. While power flows through the conductors A, power is consumed in these conductors by conversion into heat, represented by I squared R. This, however, is not all, but in the space surrounding the conductor certain phenomena occur. Magnetic and electrostatic forces appear. The conductor is surrounded by a magnetic field, or a magnetic flux, which is measured by the number of lines of magnetic force phi. With a single conductor, the lines of magnetic force are concentric circles, as shown in Figure 8. By the return conductor, the circles are crowded together between the conductors, and the magnetic field consists of eccentric circles surrounding the conductors, as shown by the drawn lines in Figure 9. An electrostatic, or, as more properly called, dielectric field, issues from the conductors, that is, a dielectric flux passes between the conductors, which is measured by the number of lines of dielectric force psi. With a single conductor, the lines of dielectric force are radial straight lines, as shown dotted in Figure 8. By the return conductor, they are crowded together between the conductors, and form arcs of circles, passing from conductor to return conductor, as shown dotted in Figure 9. The magnetic and the dielectric field of the conductors both are included in the term electric field, and are the two components of the electric field of the conductor. 8. The magnetic field or magnetic flux of the circuit, phi, is proportional to the current, I, with a proportionality factor, L, which is called the inductance of the circuit. Phi equals L times I. The magnetic field represents stored energy W. To produce it, power, P, must therefore be supplied by the circuit. Since power is current times voltage, P equals E prime times I. To produce the magnetic field phi of the current I, a voltage E prime must be consumed in the circuit, which with the current I gives the power P, which supplies the stored energy W of the magnetic field phi. This voltage E prime is called the inductance voltage, or voltage consumed by self-induction. Since no power is required to maintain the field, but power is required to produce it, the inductance voltage must be proportional to the increase of the magnetic field. E prime equals d phi, dt. Or by equation 1, E prime equals L di dt. If I and therefore phi decrease, di, dt and therefore E prime are negative. That is, P becomes negative, and power is returned into the circuit. The energy supplied by the power P is W equals integral P dt. Or by equations 2 and 4, W equals integral L I di. Hence W equals half L I squared, is the energy of the magnetic field phi equals L I of the circuit. 9. Exactly analogous relations exist in the dielectric field. The dielectric field, or dielectric flux, psi, is proportional to the voltage E, with a proportionality factor, C, which is called the capacity of the circuit. Psi equals Ce. The dielectric field represents stored energy, W. To produce it, power, P, must, therefore, be supplied by the circuit. Since power is current times voltage, P equals I prime E. To produce the dielectric field psi of the voltage E, a current I prime must be consumed in the circuit, which with the voltage E gives the power P, which supplies the stored energy W of the dielectric field psi. This current I prime is called the capacity current, or, wrongly, charging current or condenser current. Since no power is required to maintain the field, but power is required to produce it, the capacity current must be proportional to the increase of the dielectric field. I prime equals d psi, dt, or by equation 6, I prime equals cd, e dt. If E and therefore psi decrease, d, e dt, and therefore I prime are negative, that is, P becomes negative, and power is returned into the circuit. The energy supplied by the power P is equal to integral P dt. Or by equations 7 and 9, W equals integral C, E dE. Hence W equals 1/2 C, E squared. It is the energy of the dielectric field psi equals C, E, of the circuit. As seen, the capacity current is the exact analogy, with regard to the dielectric field, of the inductance voltage with regard to the magnetic field. The representations in the electric circuit, of the energy storage in the field. The dielectric field of the circuit thus is treated and represented in the same manner, and with the same simplicity and perspicuity, as the magnetic field, by using the same conception of lines of force. Unfortunately, To a large extent in dealing with the dielectric fields, the prehistoric conception of the electrostatic charge on the conductor still exists, and by its use destroys the analogy between the two components of the electric field, the magnetic and the dielectric, and makes the consideration of dielectric fields unnecessarily complicated. There obviously is no more sense in thinking of the capacity current as current which charges the conductor with a quantity of electricity, than there is of speaking of the inductance voltage as charging the conductor with a quantity of magnetism. But while the latter conception, together with the notion of a quantity of magnetism, etc., has vanished since Faraday's representation of the magnetic field by the lines of magnetic force, the terminology of electrostatics of many textbooks still speaks of electric charges on the conductor, and the energy stored by them, without considering that the dielectric energy is not on the surface of the conductor, but in the space outside of the conductor, just as the magnetic energy. 10. All the lines of magnetic force are closed upon themselves, all the lines of dielectric force terminate at conductors, as seen in Figure 8. And the magnetic field and the dielectric field thus can be considered as a magnetic circuit and a dielectric circuit. To produce a magnetic flux phi, a magnetomotive force F is required. Since the magnetic field is due to the current, and is proportional to the current, or, in a coiled circuit, to the current times the number of turns. Magnetomotive force is expressed in current turns or ampere turns. F equals Ni. If F is the mmf, L the length of the magnetic circuit, energized by F. Small f equals F divided by L, is called the magnetizing force, and is expressed in ampere turns per centimeter, or industrially sometimes in ampere turns per inch. In empty space, and therefore also, with very close approximation, in all non-magnetic material, F ampere turns per centimeter length of magnetic circuit make, H equals 4 pi times magnetizing force F. 10 to the minus 1 lines of magnetic force per square centimeter section of the magnetic circuit. Here the factor 10 to the minus 1 results from the ampere being 10 to the minus 1 of the absolute or CGS. Unit of current. Note: the factor 4 pi is a survival of the original definition of the magnetic field intensity from the conception of the magnetic mass. Since unit magnetic mass was defined as that quantity of magnetism which acts on an equal quantity at unit distance with unit force. The unit field intensity, then, was defined as the field intensity at unit distance from unit magnetic mass, and represented by one line, or rather tube, of magnetic force. The magnetic flux of unit magnetic mass, or unit magnet pole, hereby became 4 pi lines of force, and this introduced the factor 4 pi into many magnetic quantities. An attempt to drop this factor 4 pi has failed, as the magnetic units were already too well established. The factor 10 to the minus 1 also appears undesirable, but when the electrical units were introduced the absolute unit appeared as too large a value of current as practical unit, and 1/10 of it was chosen as unit, and called ampere. H equals 4 pi times magnetizing force F. 10 to the minus 1 is called the magnetic field intensity. It is the magnetic density, that is, the number of lines of magnetic force per centimeter squared, produced by the magnetizing force of F ampere turns per centimeter in empty space. The magnetic density, in lines of magnetic force per centimeter squared, produced by the field intensity H in any material is B equals mu times H, where mu is a constant of the material, a magnetic conductivity, and is called a permeability. Mu equals 1 or very nearly so for most materials, with the exception of very few. The so-called magnetic materials, iron, cobalt, nickel, and some alloys and oxides of iron, manganese, and chromium. If then A is the section of the magnetic circuit, the total magnetic flux is phi equals A times B. Obviously, if the magnetic field is not uniform, equations 13 and 16 would be correspondingly modified. F in 13 would be the average magnetizing force, while the actual magnetizing force would vary, being higher at the denser and lower at the less dense parts of the magnetic circuit. F equals dF/dL. In 16, the magnetic flux phi would be derived by integrating the densities B over the total section of the magnetic circuit. 11. Entirely analogous relations exist in the dielectric circuit. To produce a dielectric flux psi, an electromotive force E is required, which is measured in volts. The EMF per unit length of the dielectric circuit then is called the electrifying force or the voltage gradient, and is G equals E over L. This gives the average voltage gradient, while the actual gradient in an ununiform field, as that between two conductors, varies, being higher at the denser, and lower at the less dense, portion of the field, and is G equals D, E dL. K equals G over 4 pi then is the dielectric field intensity, and D equals kappa K would be the dielectric density, where kappa is a constant of the material, the electrostatic or dielectric conductivity, and is called the specific capacity or permittivity. For empty space, and thus with close approximation for air and other gases, kappa equals 1 over v squared, where v is the velocity of light. It is customary, however, and convenient, to use the permittivity of empty space as unity, kappa equals 1. This changes the unit of dielectric field intensity by the factor 1 over v squared, and gives dielectric field intensity, K equals G over 4 pi v squared, where kappa equals 1 for empty space, and between 2 and 6 for most solids and liquids, rarely increasing beyond 6. Dielectric flux then is psi A times d. As seen, the dielectric and the magnetic fields are entirely analogous, and the corresponding values are tabulated in the following Table 1.